Dear students, right now we are studying about the multiplex systems in telemetry systems, and in that series previously we studied about the pulse modulation, sampling and TDM PAM. When we are talking about TDM PAM means we are taking the time division multiplexing as the multiplexing technique and pulse amplitude modulation for the modulation purpose, and combinedly it will make a time division multiplexed pulse amplitude modulated system which is used in telemetry systems. As I told you in the previous lecture, various modulation techniques such as pulse modulation, PPM, PWM or PCM or DPCM can be used for the multiplex systems. In this context, today we are concentrating on pulse code modulation. When we are talking about pulse code modulation, it is also known as analog to digital conversion. In the previous techniques, when we are talking about pulse amplitude modulation, what we are doing? Actually, we are taking a analog signal as message or baseband signal. Then we are using a pulse to modulate the analog signal, and after the modulation we are getting some this kind of signals as pulse amplitude modulated signal. But when we are talking about the pulse code modulation, it is also known as analog to digital converter, because in this we are not actually taking a carrier signal, rather than we are directly taking this analog signal and converting it into a digital signal, means 1 0 1 0 1 0 1 0 1 0 form. So, how can we do this? For starting this, you can easily understand by this. In pulse code modulation, analog voice data must be translated into a series of binary digits before they can be transmitted. Means you are getting this signal, you are converting it into series of binary bits and then you are transmitting it. In pulse code modulation, the amplitude of the sound wave is sampled at regular interval and translated into binary numbers. But the basic difference between the original analog signal and the translated digital signal is quantizing error. These all are the main points, but when we want to concentrate on the basic technology or basic method of pulse code modulation, we have to understand this diagram. Means whenever you want to convert any analog signal, this one, into the digital data, you have to follow 3 steps in pulse code modulation, that are: first one is sampling, second one is quantizing and third one is encoding. Now, we talk all about these blocks one by one. When we are talking about sampling, as you know that this is a analog signal and we want to convert it into the 1010 form. This is in the discrete signal. So, our first requirement is we have to convert this into discrete one. For conversion of analog to discrete one, we use the process of sampling, and for the sampling you have to take care of certain criteria, certain procedures that you have to follow the Nyquist criteria, which told that Fs is greater than equal to twice of Fm. Means if we are taking a Fm frequency signal of analog signal and we are sampling this signal with the Fs frequency, means the sampling frequency is Fs, then the Nyquist criteria said that to avoid aliasing, I told you in the last lecture, aliasing, to avoid aliasing you have to follow this Nyquist criteria. It says that your sampling frequency must be always greater than equal to twice of Fm. Then by this process we perform the sampling and we will get the samples, means if I am here, I am applying x t signal, then after sampling I am getting the x and t s signal. NTS represents the samples. So, when we are getting this x and t s signal, means you can easily understand here that this is our analog signal. After taking the samples, these are the samples, these are the samples, and you can easily understand here one point, that these all samples have some instantaneous value of this message signal. So, what we have to do? Now, we have to classify these all samples. To classify all these samples, what we are going to do here? We are going to use this quantizing process. So, the picture arises, what is quantizing or what is quantization? Basically, in the quantization process, you take the samples or you take a single sample and then you compare that sample with the existing number of levels and compare them. After comparing, you give a particular level to a particular sample, and after that we get the quantized output. How it is going to be done? You can easily understand here that if this input analog signal have the maximum value of magnitude is xm, then the complete amplitude range is 2xm, that comes from xm minus xm, means 2xm. What we are going to do? We are going to divide this 2xm into L number of levels with equal interval. That equal interval known as the step size. Step size means this complete range is divided into equal step size and we get L number of levels. Then what we are doing? These L number of levels you can easily understand here. If this is our scale diagram, what you are doing here? You are creating the levels. These are the levels, various levels. And now, if this is the sample signal, what you are doing here? You will take this first sample and compare this with these existing levels from minus xm to plus xm, and then what will you do? You will round off the value of this sample and assign the nearest level to this sample. So, you can easily understand here that this first sample is assigned this level. Similarly, the second one is assigned this level, third one is assigned this level, fourth one is assigned again this particular one, the fifth one is again this one. It means after the quantization process, you get this x and Ts value as XQNTS. This is the quantized output. This is the quantized output. What so you can easily understand here that this is our analog signal. You are performing the sampling and getting this PAM signal, that is basically sampled signal XNTS. Then we are performing the quantization on this PAM signal. You are taking the complete number of levels and assigning these level to individual samples and getting the XQNTS signal at the output. Then these XQNTS, or we can say that quantized output, is now encoded. For encoding you use new number of bits, and how these number of bits are selected, that is a formula, that L is equal to 2 the power nu. Means if you are taking 4 individual levels to quantize the available samples, then the number of bits are 2 the power 2, means nu is equal to 2. Similarly, if the number of levels are 8, then number of bits are 3. If the levels are 16, number of bits are 4. Similarly, you can calculate the number of bits as per the number of levels, or you can also understand it, if you are taking the 2 bits, means you have 4 levels and each level have a distinguished code as 00, 01, 10 or 11. In the case of L is equal to 3, means 3 levels, you have codes 000, 100 or maximum 111. It means you are going to compare, you are going to take this XQNTS value and going to perform the encoding for that individual quantized output, and you will get this quantized encoded output in the form of 11000011. It means this is the basic PCM working. To understand it more clear, so now as we understand about the pulse code modulation, that in pulse code modulation actually we perform 3 steps, that are quantization, then encoding, and before that the sampling. So, by using these 3 steps we perform the pulse code modulation. So, always remember to identify the number of level, we use this formula where del is the step size and 2xm is the complete amplitude range. For the number of bits, we have L is equal to 2 the power nu, where nu is the number of bits used for the pulse code modulation system. So, now understand this pulse code modulation system with the time division multiplexing, because in telemetry system we are actually design the multiplex system, and here we are talking about the digital multiplex system. So, we are using a digital multiplexing technique that stand for time division multiplexing, the digital modulation technique, that is pulse code modulation, and combinedly we are taking this digital multiplex system used for the telemetry principles. So, what will happen here in the context of telemetry, if we have n number of sensors at the remote location, each sensor giving us the input from channel 1, channel 2, channel 3, so on, n number of channels. Then these inputs are applied to a sampler switch or a commutator switch. This commutator switch will perform 2 functions. First one is time division multiplexing as well as the sampling. After performing the sampling and the time division multiplexing, where this commutator switch have a rotating arrow switch that is connected with the clock signal or the governed by the input sampling frequency. Then we are giving this sampled output to the quantizer and encoder, and that quantizer and encoder giving us the TDM PCM signal. Now, as soon as this time division multiplex pulse code modulated signal left this transmitter part, it will go through the channel, and you know that in channel, whether it is a wireless or a wire channel, always noise is present and noise is additive in nature. So, that noise will be added in this TDM PCM signal. Now, this noise added TDM PCM signal is applied to the receiver side, where the reverse process of PCM encoder side will be done. Means, first of all you perform the decoder, you means decoding of the signal, and you will get the quantized output. Then you will get the quantized output and perform the sample and hold circuit through a decommutator switch, and we will get the various channel output or the baseband signals. Also, the low pass filter for individual channel is also applied here to remove the other signals or other unwanted signal for a individual output. So, you can understand here one point, in the PCM system you have three major parts, that are transmitter, the channel and the receiver. So, in the pulse code modulation system we have this complete diagram. This is giving us a complete picturization of the pulse code modulated system. Here you can understand by this that very first you are applying a analog input signal which on through the channel 1, and that is applied to a anti-aliasing filter. Why we are using this anti-aliasing filter here? Because the first step of the pulse code modulation is sampling, and in the sampling process we always have to consider one step or one criteria of Nyquist criteria, that is Fs is greater than equal to twice of Fm. Means if Fs is less than twice of Fm means aliasing will be there, and to avoid that anti-aliasing filter is used. Then that anti-aliasing filter output it applied to a sample and hold circuit, where a 8 kilohertz sample pulse for a 4 kilohertz channel 1 input can be used. You can easily identify the here point that here the Fm is 4 kilohertz, whether the sampling frequency is 8 kilohertz, means twice 4 into 2 8 kilohertz. Then this sampling frequency or sample and hold circuit will create a sampled output, and that sampled output will give the PAM signal. That PAM signal is applied to a analog to digital converter. That analog to digital converter basically have quantizer and encoder. Means you are performing here the quantization, after that you are getting the encoded output. Then what will happen? You can see here, if you are getting a XQ NTS signal at this signal, this particular part, after quantization when you are performing the encoding on this, you will get for example 1101 for this individual quantized sample. But you can easily understand one point, that this 1101 will generate on the same time. Means as soon as X NTS signal will enter here, you will get here 1101. Means this encoded parallel PCM code will be generated, but you know that on the channels data will be transmitted serially. So, you have to convert this parallel data into the serial one. That is why you are using a parallel to serial converter, means now you are sending this 1101 in this form. Then this converted 8-bit serial PCM code on a 64 kbps bit rate, you will send this, and this will go to the TDM multiplexer and then the channel. At the receiver side, what will happen? As soon as you will go from here towards the receiver, the reverse process will be done. Means at the receiver side, what will happen? You first of all you convert the serial data to parallel data, then you will decode that data, means digital to analog conversion, and then again you are using a sample and hold circuit to get the baseband signal back. So, this is the transmitter part, here we are talking about the channel, and this is the baseband receiver part. So, this is about the TDM PCM system. In TDM PCM system, you can identify one very important fact, that is bit rate and the bandwidth. Bandwidth is of PCM signal is basically related with the number of bits used, that NB or nu, that is the just a difference of the notation. NB is equal to number of bits, means if your message signal frequency as per the previous slide 4 kilohertz and you are using 2 bits to encoded this signal, then the bandwidth will be 8 kilohertz, or bit rate is the 8 kbps. So, the bandwidth required to transmit this signal depend on the type of line encoding system, and the digitized signal will always need more bandwidth than the original analog signal. This is the main disadvantage of the PCM signal, that as soon as the number of bits will increase, bandwidth will also increase. So, this is the biggest disadvantage of the pulse code modulated systems. To remove this problem or to compensate this bandwidth requirement, some derived digital modulation techniques can be used further, in which delta modulation, adaptive delta modulation and DPCM are most common. So, in the next lecture we will concentrate on the differential pulse code modulation technique, that stand for DPCM. Till then, thank you.